Let's take a look at antimicrobial drugs. That's chapter 20 in your textbook. We're going to start out with a little bit of history here on the chemotherapy. Some terms that you need to know include selective toxicity. That's a big issue because it means that you want to find a drug or substance that selectively kills microbes but doesn't do much harm to you, or if any, to your body. So when it comes to antimicrobial drugs, of course, it would be easy to find a substance that will kill bacteria, but then it might cause damage to your cells, and obviously that would be bad. Chemotherapy is the term that we use when we just want to say that there's a chemical that's used to treat a disease. Antibiotics, anti means against, bios is life, so it's a substance that will inhibit the growth of, for example, microbes. So a lot of times these antibiotics, they are produced by other microbes to give them an advantage over the microbe that they want to hinder in their growth. Antimicrobial drugs, those are chemicals that usually the beginning is a natural substance, and then you modify them in the lab and make synthetic chemicals out of them that then can be used as antimicrobial drugs. The history of chemotherapy, of course, Alexander Fleming's important discovery on penicillin. So he was making the observation in the lab that a plate that accidentally grew some mold, penicillium mold, that surrounding the mold there was no bacterial growth. And that observation eventually led to the discovery of the very first antibiotic, which is penicillin. Then 1932, Prontazil, was used for streptococcal infections, and then 1940 came the first clinical trial of penicillin. And of course, penicillin, that was the starting point for all the antibiotics that were developed. Now, nowadays, well, let me back up. After the discovery of penicillin and when it became available for people to use, everybody thought, oh, we now got the miracle drug and we will never have the issue of microbial and bacterial infections anymore. Well, as it turns out, nowadays, bacteria, they are smart. They have now developed resistance, and resistance is becoming a growing problem. There are many multi-drug resistant bacterial strains out there that cause big problems in hospital settings. Let me show you a plate where you can sort of evaluate the effectiveness of an antibiotic or an antimicrobial substance. If you find something like this here, where there's the blue circle around, there's let's say a little disc, and you have added some substances in it, and now you see that the bacterial lawn is disrupted by this area of clearing, that would be an indication that whatever you put onto this little disc right here has an antimicrobial effect. Same would be true for over here. There's a nice zone of clearing. All right, let's take a look at some representative sources of antibiotics. Some microbes, including, so that would be other bacteria and fungi, they can produce antimicrobial substances. So here in the class of positive rods, we have Bacillus subtilis making the antibiotic bacitracin, Panobacillus polymixa making polymyxin. These two antibiotics are usually used in triple antibiotic ointments, so they are used more externally. And then we have a bunch of Actomyceta species, so Streptomyces species that make various antibiotics. You can take a look at that. And then fungi, big one here, of course, Penicillium, making penicillin or Griseovulvin. And then we have Cephalosporium species and making cephalosin. We will take a look at some of these antibiotics and how they work later. Now, the spectrum of antimicrobial activity refers to the range of bacteria or microbes that an antibiotic affects. A narrow spectrum means that you're affecting a very narrow range of microbial types. Broad spectrum means that you're affecting a broad range. For example, broad spectrum would be something that affects both gram-positive and gram-negative bacteria. Superinfection is the term that we use when you have overgrowth of normal microbiota that's resistant to antibiotics. So that means you've probably overused antibiotics, and now the normal microbiota is resistant to antibiotics and is kind of taking over. Here, the spectrum of activity of antibiotics, you can just take a look at that. Let me just point out a couple of things here. Tetracycline is very well known as a broad spectrum antibiotic. Take a look at the range here. So you're spanning both gram-negative, gram-positive bacteria, even the intracellular parasites, the chlamydias, rickettsias are affected. Then penicillin G will be a relatively narrow spectrum antibiotic. So you can just take a look at this chart right here. The action of antimicrobial drugs. So the terms you need to know here are bactericidal. Cidal refers to killing. So this one kills the microbes. Bacteriostatic prevents microbes from growing or slows down their growth. The antibiotics are in this category. They're bacteriostatic. They hinder the growth. So here we have an overview slide of how antimicrobial drugs work. Here, number one would be inhibition of cell wall synthesis. So that means these types of antibiotics, they will, they will weaken the bacterial cell walls, and thereby then the contents will leak out and these bacteria will not be able to multiply. In this category, we have the penicillins, cephalosporins, bacitracin, and vancomycin, all very important antibiotics. Next will be inhibition of protein synthesis. And there we have chloramphenicol, erythromycin, tetracyclines, streptomycin, also very important class of drugs. And so there we are interfering right here, inhibition of protein synthesis. So that these antibiotics typically bind to the ribosome and hinder then protein synthesis. Next one, here on 3, down here, inhibition of nucleic acid replication and transcription. This will be quinolones, rifampin, also important. And then number 4, injury to plasma membranes, polymyxin B. That's usually most used topically in ointments. And then here on 5, we have inhibition of essential metabolite synthesis, sulfonamides, trimethoprim. That will be in this category. Okay, so let's start with number 1, the action of antimicrobial drugs that inhibit cell wall synthesis. That will be the penicillins, and they prevent the synthesis of peptidoglycan, which is, as you know, an important component of bacterial cell walls. And so here we have a figure that shows the effect of penicillin on cell walls. Here would be the bacterium before penicillin treatment, and then here we have the bacterial cell wall. Lysing is damaged, obviously, because penicillin has weakened the cell walls. Another important class are the antibiotics that inhibit protein synthesis, and they will target the bacterial type of ribosome, which is the 70S ribosome. We have covered this before in lecture, pointing out that the bacterial ribosome is a 70S ribosome versus the eukaryotic ribosome is the 80S ribosome. And while it may not seem like a big difference to you, but it's enough to where you have selective toxicity, because these antibiotics, chloramphenicol, erythromycin, streptomycin, tetracyclines, these antibiotics, they will bind to the bacterial ribosome while leaving the eukaryotic ribosomes alone. And so here's what this looks like. There are different antibiotics shown here and how they interfere at the ribosome as it's translating messenger RNA into protein. Let's start out with chloramphenicol. This antibiotic binds to the 50S portion of the ribosome, so it would be the larger subunit of this ribosome right here, and inhibits the formation of the peptide bond. So that would be the bond between each amino acid. Tetracyclines, they interfere with attachment of the tRNA to the mRNA ribosome complex. That would be right here where the tRNA comes in. And streptomycin changes the shape of the 30S, the small subunit of the ribosome, and causes the code of the mRNA to be read incorrectly. Both tetracyclines and streptomycins are very popular antibiotics. Chloramphenicol not so much, because this one has a lot of side effects. Here, antimicrobial drugs that injure the plasma membrane. And here that we have polypeptide antibiotics that change membrane permeability. There are also some antifungal drugs. Of course, if you're interfering with plasma membranes, then eukaryotic cells have plasma membranes as well. So antifungal drugs, they combine with membrane sterols. Here we have a yeast cell that was treated with an antifungal drug here that is injuring the plasma membrane of this yeast cell. Now, the last two groups of antimicrobial drugs are those that inhibit nucleic acid synthesis. That's these here. So they interfere with DNA replication and transcription. And then we have those antimicrobial drugs that inhibit the synthesis of essential metabolites. What comes to mind is that, for example, the sulfonylamides, they compete with para-aminobenzoic acid, PABA, and stop the synthesis of folic acid, which is an essential metabolite. Now here comes a long list of antibacterial drugs, and I'm just going to point out some of the very important ones. So on this list of antimicrobial drugs, let's just kind of go through the list, and I'm going to point out which ones are important for you to know. So we're starting again with the inhibitors of cell wall synthesis. There will be the natural penicillins. These are the ones that it all started with. Then the semi-synthetic penicillins. So these were modified in the lab. So they started out as natural penicillins, and then they were modified. There are some important antibiotics that I'm sure you've heard about: oxacillin, ampicillin, amoxicillin. Those are all very important. So these three here you should definitely know. The cephalosporins you should know as a group. No specific ones necessary here, but as a group you should know this about the cephalosporins. And then polypeptide antibiotics, bacitracin and vancomycin. You should know these two by name. Then antimicrobial antibiotics, those you should just know as a group. Again, no specifics. And then moving on to the inhibitors of protein synthesis, chloramphenicol you should know by name. It is not very often used because it has a lot of toxicity and side effects on people that are taking it. So it would be a last resort to take it, but you should nevertheless know about it because it's important in its activity, how it works. Then we have aminoglycoside drugs, and those you should know by name: streptomycin, neomycin, gentamicin. All of them would be important right here. These are all very important antibiotics. And here, moving on to inhibitors of protein synthesis. In this group, you should definitely know about the tetracyclines. Tetracycline is a very important antibiotic. You should also know about the macrolide antibiotics, specifically erythromycin and azithromycin. Most of you have probably taken azithromycin, the Z-Pack. It's very convenient because you only have to take one pill a day, and that's because it has a much longer half-life. Now, what we can take off of the list of important antibiotics for you to know would be this first group right here: streptogramins, these guys here and these guys here, so not so important for you. And then injury to the plasma membrane, we have the polymyxin B, which we already mentioned previously, but you don't need to know about these guys. So just the polymyxin B in this category. Inhibitors of nucleic acid synthesis, you should know the rifamycins. Rifampin is the drug. And then lastly, the quinolones. There you should just know as a group that they exist. and competitive inhibitors of the synthesis of essential metabolites, the sulfonamides. You should definitely know about sulfonamides. That would be an important group of antibiotics.